Kurt is delivering those files to you via a low bandwidth Ethernet. Okay, so we're going to start with one that you already have, and we'll work to incorporate the ones that he's going to be placing on there. Within the Dropbox, you will find example models and specifically go into generic example models. And one of them would be this one. There's a thing called CTL state variable. Use AnyLogic 7 there. This is perhaps the 15th down or so from the top. If you could open that, we'll see. This is a very simple model which depicts the ability to. Oh, okay, that's great. Let me open it within AnyLogic. It depicts a situation where agents are characterized. Agent dynamics are characterized using stocks and flows. Specifically, you see here a person is defined, their evolution is defined according to a state chart, but also according to a series of stocks and flows. These stocks and flows depict their immune system status and the variability in their immune system status over time. Most notably, it captures phenomena like waning of immunity over time and the buildup of immunity in response to infection. So each individual here has aspects of their immune dynamics characterized with stocks and flows. This is AnyLogic's depiction of stocks and flows. And a notable feature of this is that there's an inflow from other individuals, from other people. And these are people in the network. So the actual flow in here is dictated by the formula for this flow, which is omega times viral load of neighbors. And this thing, viral load of neighbors, is in turn defined as a function, total viral load of neighbors, which we can find over here, which basically goes through all neighbors and totals up their viral load. So fundamentally, we have each individual evolving over time according to stocks and flows, and infection spreading from one person to another via a network. That total viral load of neighbors is computing. It's getting each person in their connections in a network. So let's run this model, and let's specifically run the high fatal viral threshold here. So it says high fatal viral threshold, and if we run this, we'll see individuals placed into a network, and you can see an index individual getting infected. I'll slow this down. And the infection is spreading across the network over time. So these people are getting infected now. The redness indicates the amount of free virus that they have circulating, and the size of the circle indicates their immune response to that. So you see the infection spreading across this network from individual to individual. And over time, individual status evolves. There's actually some oscillations, some sort of secondary growth in the level of viral load within a given person. Here we have a hybrid model, hybrid because we have agents. Each of those agents are placed in a network, and within each agent, we have stocks and flows, system dynamics components, as well as a state chart here. Now this state chart over the left, you'll notice, uses a transition you may not have seen before, this condition transition. And what that says is if the viral load within that person, this V stock, which is one of these stocks over here, that exceeds a given threshold, then they die. So if their viral load goes too high, they die. Individuals within this model, I believe, moreover, differ with respect to their immune system strength. So we have these various parameters down here. that relate to immune system strength. And these parameters, and this is actually response to the immune system here, these parameters can be drawn from random distributions. They can also be dictated for the population as a whole here. So, for example, the value of C here is parceled out to individuals as being between a uniformly distributed variable between 0.3 and 1.1. So in other words, people are placed in this network with different levels of immune strength, okay? And they evolve according to these stocks and flows within a given person. So a given person here, if we were to run this again, we'll run this model, and we will drill down to the level of a particular person, say person 0, and you'll notice that this person has a value of C that's 0.885, this other person 1.074, this other person 1.058. So there's a variety of different levels of immunocompetence, and that leads to differential ability to control the infection within an individual. The individual is, over time, evolving with these stocks and flows, and we can see this here by clicking on a stock and pressing this, I'll do it again, by clicking on a stock here and pressing this button here, we can capture their evolution over time in terms of that particular stock. So you'll notice that their level of immune response is varying continually over time in accordance with their particular features. If we were to modify their level of immune response, we can do that through this interface by clicking on one of these parameters and doing this. If we were to give them a very strong immune response instead, say of 2.0, now we see that it's materially affected their immune response. If we were to make it very large, I believe we would see a very different pattern yet. So in any case, here we have individuals in a network that is characterized as in classic agent-based modeling form, but we have their dynamics described both according to state charts, over here to the left, as well as by stocks and flows over here to the right. One advantage of the system dynamics approach is that it's mostly declarative. So we just specify, as I commented in my lecture, we specify the formulas here, and it will make it happen. There's very little in the way of actual coding that's required for the system dynamics, very little in the way of sort of programming. No semicolons here for the most part. Okay, so this is individuals there. The basic mechanisms you will have seen before for the agent-based modeling components. For example, how do you think people within this model, how do you think we made it so that their the size of their circle depended on their viral load? How do we do it so that the size of the circle depended on their level of immune response? How do you think we accomplished that? Where do we go in this model to see that? So the size of the oval, right, for that particular person. And let's go over here. Hey, where's their oval? Where is their oval? Let's go look where their presentation is. This is a useful life skill with AnyLogic. You click over here. Oh, it looks like their oval lies within that state chart. That's not very good. I'll just move it back to its rightful place. You'll notice that their radius of their oval is just given as 5 times z, and where z, I guess I should say z here, where z is given by this here. It's this stock. So their z value, which gives their level of immune response, is used to set their radius, and then the actual color of the circle is set with people color. And people color is a variable that's determined over time. We could actually do a better job with this with the newer versions of AnyLogic. It's very, very easy to have it just have a nice little formula here that specifies how their color varies within some range. Okay, anyway, this is one example model. We have system dynamics within agents. Any questions on that? Yes. Right. That would be a common motivation for it, that if there's some quantity of that person that's continuous in character, and you want to capture dynamics of that quantity over time, its variability over time in some sort of regular way. System dynamics model will be a tempting way to accomplish that. It's not the only way, but it's a very tempting way because it's specifically well adapted to describing the evolution over time of a system whose state whose variables dictating their current situation are continuous in character. Now, of course, we've seen before many models where they have variables or parameters which are continuous. An example might be a birth weight, right? Or an example might be their birth date expressed as a year. Or height, right, would be another one. And in those cases, really there may not be a need to represent it as stocks and flows because it's just a static quantity. If it varies over time in a continuous fashion, it's rising and falling in a continuous way, it's very tempting to characterize it with stocks and flows. I have also participated in other models together with microsimulation folks, for example, where they have continuous variables for like health state expressed between 0 and 1 of a person, and it just it's a double precision value, but it gets updated once a year, and that's another way to do it. But if you want it sort of gradually updated all throughout the time, as say due to caloric intake and expenditure, or due to exposure to bad air quality, your lung function changes, then stocks and flows are a pretty tempting way to do it. I won't say they're required, but they're certainly a powerful way to do it. Is that helpful? Okay. Yes. That's a good question. If I wanted to capture the equivalent situation of stocks and flows, using only if I didn't have access to a stock and flow palette here, and I wanted to manually create stocks and flows in AnyLogic, would it take a lot more time? Yeah, it would take a lot more time, but more to the point, it'd be more error prone too. I could easily make mistakes. Having recourse to kind of these stock and flow representations means that a lot of things are taken care of for me, and there's less chance I'll make a silly mistake when implementing it. It would require more technical finesse for me to do it myself, considerably more. If you're talking about could I describe any dynamics for it, maybe dynamics, it's not that maybe again once a month we update someone's viral load based on some formulas. Yeah, I could do that pretty readily. The question I would ask is there a theory there? Because theory making with differential equations is very well established, and so we'd want some sort of kind of grounding for whatever equations we put in to make sure we weren't just sort of pulling them out of thin air. And again, differential equations are a very well accepted way of describing things. We kind of know how to analyze them. So they're tempting, but yes, I could do a very basic thing. Have an event go off every week, and it updates someone's viral load based on the viral load of the people around them. That would be pretty straightforward to do. It's just it might not be as theory driven, like that. I mean, this model that we're using here is a published model, and in fact, I think some of the citations for it were shown on the example of the model. So the point is, we used recourse to that because it's sort of accepted practice in that area to have models of the immune system that are grounded in that sort of way. Is that helpful? Yeah. Okay. Very good. Okay. So folks, I'd like to close that model, and we don't need to save it. Um, although, yeah, I should have shown you, if you had run some of the other experiments, you would have seen people die. They disappear from the network when they hit a level of threshold of infection. That might have been interesting. Okay, let's open another model in that same folder. Kurt, is that uploaded or? Okay, thanks very much. Much appreciated. Okay, I'm going to open a model that builds on that same basic idea. There's another flu immunoepi, which is a model grounded via work with a flu immunologist with laboratory data incorporated. It's a more fancy version. It sort of draws on the same basic approach as the one we just saw, so I'm not going to go into it. But if anyone's interested, you can go look at that. Let's go look at, there's a model, gridded system dynamics model. Here, gridded system dynamics with edit box. I think this is the appropriate one, the two with very similar names. The idea here is very similar, ladies and gentlemen, in the sense that we have agents, and each of the agents is described with system dynamics. And so if we go here and we go to system dynamics, oh, okay, sorry, this is the wrong one, but it'll do. Here we go. Oh, this is horrible. This is horrible. Oh gosh, yeah, this is more. It's big, and it'll be maybe a bit hard to understand how it works. So I'm just going to open the other one. I'm sorry about that. I'm just going to open this one just above it in the examples. It's called Gridded System Dynamics using AnyLogic 7. Sorry about that. I think this is the appropriate one. Okay, so here we have agents, and the agents represent patches in space, and each patch is described, and this is why I'm choosing this, because it's a very simple little model. The other model actually had a empirically grounded model of West Nile infection in our province. It's interesting as an example of a empirically grounded model based on a lot of data, but the organization visually is kind of confusing. So I'm going to show you this one. Each patch here is dictated in a very simple way by system dynamics. This is just a simple model with some heuristic little things to show how it works. And then in the main class, what we have is an environment that's a discrete environment, meaning we have a bunch of patches. And if you go to main and you scroll down, you'll see we're in a discrete environment. We have a certain number of patch columns, a certain number of patch rows, and we have the agents arranged in a regular grid. So let's take a look at each patch. Each patch is dictated according to these stocks and flows. And here, up in the upper left, we have a rectangle whose color is set by a formula. Okay, and that formula will vary continually because it's based on the values of these stocks, which are varying continually. So the value returned for the fill color will vary continually because it's based on this stock here. Okay, so I'm going to run this model, and what you'll see is a depiction over space. This is just showing these patches. They're actually abutting each other, but they're visually shown as a little bit smaller. And each of them has some number of organisms in it, and the organisms go through to a mature state, and there's migration. There's migration from one patch to another. And so over time, you see these spreading, and you can see them interacting over time. So this is a situation, you can see these kind of waves of movement there. This is a situation where we have each patch evolution described by these stocks and flows, and the patches interact by migration of individuals from one patch to the other. Okay. personally, I really just like how it's laid out there with small patches. So you might want to try doing something more like that, and it might have greater prettiness associated with it. There we go. Oh, a thing of beauty. Okay, so here the patches are evolving, and they're each being dictated by a system dynamics model, right? Okay, so we have coupling between patches through this flow, and each agent its evolution is dictated in this way. So when you have, per Rock's question, when you have agents whose dynamics vary in a continuous way, system dynamics modeling can be very fruitful for describing those elements of the dynamics. But you can also have state charts. You can also have parameters. You can also have other types of calculations going on. It's just for certain variables you might want to use stock and flows. Okay, so that's gridded system dynamics. One of them we've seen had them in networks. This one had them in spatial layout. Same basic idea though. Agents dynamics are at least partially described with stocks and flows. Okay, let's close that model. Let's go on to a very different sort of model, and specifically, I'm going to draw on a model that's the it's called the Beifeng-Ren model here. So it's a model associated with end-stage renal disease and diabetes within our province. This is a model, we have a paper on it that will be coming out later this year. It's been accepted, and I was just doing some proof-related stuff with it. But this model is quite different. This model illustrates the integration of three types of modeling within a single model. It has some components in system dynamics. It has some components in the agent-based, and some components in the discrete event. Winchell, it's the Beifeng-Ren. Yeah, that's the formula, the folder it's in. It was constructed by people from northern China, so that's what we called it. Yeah. There are 4 people from northern China that built it, so different pieces of it, so we just thought we'd call it that. Okay, so let's go see what's going on here. So here we have 3 types of processes described with different systems. The first and maybe most central is one describing the evolution of an individual over time according to their, so these are diabetic individuals. We did a competing risks analysis to identify competing risks associated with diabetic progression to end-stage renal disease and death at the same time, and we used the results of that competing risks analysis to parameterize these transition likelihoods, these transition hazards associated with diabetes progression and with end-stage renal disease development. Now, once people developed end-stage renal disease, they go to a state where they're initially typically on dialysis, and we modeled 2 dialysis modalities. At some point, they may receive a transplant, in which case they go into a transplant-related state. We distinguish people in this transplant state according to how long it's been since they had the transplant for 2 reasons. Number one, it related to the chance of graft failure, the chance the kidney would fail. And number 2, because it related to cost. This is a model that had health economics concerns as quite an important component, and we wanted to be able to capture the differential cost associated with different dialysis modalities as well as transplant. And there are large cost differentials affecting progression for a longer and longer time with transplant. The first 90 days in the transplant operation itself are very expensive. And then later stages with transplant cost less than dialysis. There's also the chance of death at some point following end-stage renal disease. Okay, so within this model, an agent's progression was captured according to these states. Now we further, however, had a model, and I think this one is also, AnyLogic's import for Venn models is very functional, but it's very visually unpleasant. And I'm going to have to find, here it is. I mean, you can lay it out better. Okay, excuse me. Here it is. It's under SDMOL, sorry. So this just needs to be, it needs like a day of work to clean it up. And unfortunately, the Beifrangren have left our institution. Or unavailable. So here we have a system dynamics model with progression between these states, and don't be distracted by the ugliness of this, but fundamentally it's a system dynamics model, and this is very important. We capture individuals in the system dynamics model upon birth. They then progress in terms of their weight status in the system dynamics model to the point of prediabetes. At the point they develop prediabetes, if they then develop full frank diabetes, then they're turned into an agent. They're turned into an agent whose context, whose characteristics are recognized, and they flow into this model, or they become one of these agents depicted here. And they then progress through these state charts. So prior to that, they're just a number in stocks and flows. They're just one more person in this undiagnosed pre-diabetic population or in the obese population. But once they reach the point of great concern for developing end-stage renal disease, namely when they develop diabetes, and our focus here was diabetic end-stage renal disease, they become a full-blown agent. What that means is we don't have to simulate the full population as agents. We simulate most of the population as counts in a stock and flow model, and when they reach a critical point of interest, we turn them into an agent. They progress through this, through the subsequent part of their lives in this agent-based model. However, there's an aspect of their interactions that is captured with a discrete event model while they are in this state. While they're in this state of being diabetic, their interactions with the healthcare system are dictated by this. It's actually in Maine. Sorry, here. It's in Maine here, and you'll notice that if you zoom in Maine, you'll find this progression here. Fundamentally, folks, when they reach the point of end-stage renal disease, we need to reason about waiting times for transplants, waiting and assessment times, and a lot of it becomes resource limited. In other words, their progression in terms of availability of transplants is dictated by cues associated with the limited number of kidneys coming in and the demand for those kidneys. And that's a classic issue where discrete event modeling is really useful. We have a limited number of kidneys, we have a limited number of doctors to undergo surgery, to help them undergo surgery. And so for this component of the model, we use a discrete event model. The person is still an agent all throughout this, but they flow into this discrete event model as well, where they are waiting for eligibility checks for a kidney transplant. They flow through that, and then they are awaiting a transplant, and their treatment is different if they're a deceased donor or a living donor, transplant potential recipient. And for all of this, we have resource constraints represented in a way that can be done very crisply and very elegantly within the context of discrete event modeling. Discrete event modeling shines when you have individuals flowing through a system where there are resources needed to operate upon them. And that's exactly what we have here. There are resources needed in the form of kidneys resources needed in the form of surgical expertise, in the form of waiting for a doctor to do an assessment that are needed for them to flow through. So here, they are an agent as captured by this person model here, and they are simultaneously, their flow through the kidney waiting process is also going on within this context. Eventually, if they are healthy and they survive, and if there's a willing donor or a deceased donor that is been willing to give their kidney, they will actually be provided with a kidney. The kidney will be transplanted into them, and they will actually then, as a result, flow back into this transplant state. It's that receipt of a kidney that allows them to go this way. It's their flow into with end-stage renal disease that allows them to be put as a candidate for assessment for a kidney transplant. And if the kidney fails, they will also go into a reassessment process. So if they undergo that failure, they can re-enter that process of awaiting a kidney as captured through this process. Now, why do we do this? Why not just represent it all in agent-based modeling? Because all that logic, no question, could be done in agent-based modeling. It would require quite a bit of extra work and mechanism. It could lead to bugs and mistakes, and it would require a lot of time. It's just really sweet to do it in a discrete event modeling context. It's the right tool for the job. It provides the right vocabulary. It provides the right mechanism to do it in an elegant way. And it allows us to then vary assumptions about how many kidney, at what rate kidneys become available, and see it ripple through to how people's health state evolves, for example, down here at the person level. So this is a model, in short, where we have it's a tripartite model. We have three types of modeling captured. We have system dynamics modeling captured for people who are at lower risk, people who haven't developed diabetes yet. We have agent-based modeling captured those who are at risk, who have developed specifically diabetes and end-stage renal disease. And we have discrete event modeling captured the resource constraints associated with the situation. And all of this, although I'm not providing looks at this, this is a highly data-driven model. So we have data from our provincial ministries, from the Canadian Organ Replacement Registry, from our province's kidney replacement program, from a wide variety of epidemiological data sources, some primary data collected by my colleagues from the nephrology program, and those are incorporated as well in this model. But the things I want to highlight today, and there's an interesting story about some policy insights we've gotten from this model that will be coming out in a series of papers. But within this model, we've joined together the three types of modeling, with each being used for its core competency, each for its area where it shines. And system dynamics shines for simulating in a cost-efficient way. By cost, I'm talking about performance. We can very quickly sort of simulate evolution of most of the population. Agent-based modeling for capture rich heterogeneity, capturing family context, potentially geographic context of individuals, their history of past transplantation, all those sort of features we're interested in, and discrete event modeling for those resource limitations. So this Bayes-Hongren model is perhaps the most integrated model I know that incorporates, it's the only one I know that incorporates all three that I've worked with or that I'm aware of. But it's a powerful indication of what you can do by combining the three, with each being used in its kind of natural domain of application, rather than trying to force fit your entire model into only one. So any questions about that? Yeah. That one had lots of flows in it, yeah. Yeah. Right. So that's a little bit. So I can understand why you might be thrown off by that, and I would caution one thing. That system dynamics model was actually the full more complete story here is that the system dynamics model um, that was shown to you here in a somewhat abusive way was that system dynamics model was actually not originally developed for this model. It was actually a model of diabetic progression, which included those with later stage complications of diabetes in a system dynamics framework. And that was developed in Vensim until this past year. And in Vensim, it's actually very visually manageable, etc. What happened is that we realized that we were taking this agent-based model and we were taking in people from output from that system dynamics model. In other words, we were taking files output by the system dynamics model and reading them in to dictate the number of people coming into this agent-based model over time. And we said, look, why do that? We can actually import it into AnyLogic. And so that's exactly what we did. We imported it. Now, it works perfectly fine when you import it. It took about a day to import it. And when I say a day, it was mostly fixed up, having to do with the fact that it's subscripted by age, group, by sex, by ethnicity, and by, I guess those are the main ones. And that was liberating, being able to do that, because we could then run a single scenario, say, suppose you could reduce incidence of obesity. How would that ripple through to the costs associated with end-stage renal disease in our province? You can do end-to-end runs like that. And there was considerable interest in our partners in this work in the South Sudan Health region, because they were interested in what degree saving from downstream could be used to foster upstream intervention for obesity reduction based on savings from lower dialysis costs or what have you. In any event, that import occurred into here after it was developed. I would never tolerate working with the system dynamics model in here in any significant way in its current state visually. What you see there is disorienting because when you import it, AnyLogic doesn't know how to lay it out nicely, and so it does a kind of rough job laying it out. It would take about a day's work to sort of organize it. And once you organize it, it's really, not particularly worse than, one of these other models that we saw, like this one here, in terms of its layout. In other words, not that one. Sorry, I showed the wrong one. It's not particularly worse than this sort of thing by its layout. So I could show you the Vensim model, and it's actually very, very clean to work with. And similarly, it could be in Vensim, in AnyLogic. It's just that by default, the import doesn't do a particularly good job laying it out, and you can adjust it and lay it out nicely. So I think a lot of the impression there is coming from its appearance, and yeah, I probably should have gotten one of those students to work on it for a day or two to clean it up first. But as far as sort of conceptualization, it's not that complex a model. And in fact, we've removed a large part of it having to do with later stage complications of diabetes, because those are subsumed by the age-based model. Yeah. Does that make sense? Yeah. Yeah. Right. Right. Well, yeah. And once again, I would come back to my suggestion too. So again, agent-based modeling is distinguished by its flexibility. And as I've mentioned before, it's a double-edged sword. It's a great, powerful thing. It's a little bit like a power saw. Um,
PowerShell, you can do lots of great work, but you can also do lots of damage awful fast, right? You can make quick work of cutting up a log, but you can also make quick work of your arm. And you got to be very careful using a PowerShell. And there's basic, safety procedures you go through and safeguards that you put in place. With agent-based modeling, one of the most important safeguards is making sure that you build it up incrementally, and that you are very conscious about questioning this endogenous, exogenous, ignored distinction to figure out, what the next highest priority is. Because there's no question that you can throw a lot of things in and get limited inside out because of over-eagerness to arrive at something that looks like the real world, but really isn't meaningful for serving as a thinking tool. It's not bringing new insights to bear because you don't know if there's bugs in it, you don't know if it's working properly, or if you see some interesting phenomena, you don't know where it's coming from. And so really it's step-by-step building it up, disabling things that you've added, making sure it matches what you saw before, re-enabling them, doing experimentation, learning from that before deciding what to do next. This is the name of the game when it comes to agent-based modeling. That offers some help? Okay. I would emphasize again, though, my point that I made early on, and that does bear note. There's a spectrum of agent-based models out there. Some of the most powerful agent-based models are those that deliver a punch because of their simplicity. They don't incorporate, hundreds of factors. They're not seeking to say exactly what to do in a certain empirical situation, but instead they're making a point about the potential great importance of a certain interaction, and they motivate data collection, or they motivate further study of that, or they motivate, focus to building this model that's more detailed for those particular issues. And just like you can build, so the system dynamics model, it's a lot harder to get extra mechanisms in, so you're restrained by the framework more so than in agent-based modeling. In agent-based modeling, though, you can, with discipline, build very simple models, and those can give you, great insight that you can bring in a way that's operational. But you want to be conscious about what you're looking for in your model before you set out. You want to move towards it in a very deliberate, incremental way.
Okay. So the final model that I thought I'd look at here would be a model that was related to one of the projects being undertaken here, and it's a model that is called, and I'm gonna have to grab it here. It's called simplest ABM process hybrid with resource constraints. Okay, this is in contrast to models we've seen before. This deals with a different hybridization, ABM with discrete event modeling. Okay, so let's take a look at this model, and we'll see in detail how it works. This model is focused on a very common need in certain areas of the health space to examine situations where individuals in a population come into contact with the health care system, and particularly present for care in a facility, whether it's a clinic or a hospital, that has a defined process associated with it. You could also think of this as applying to situations where you have those people undergo processing in a sort of
in a more of a paperwork sort of sense with respect to handling, something having to do with VA care where you go through several stages before you're actually delivered care, but you have a defined workflow once again. Okay, so in this model we have what looks to be a very familiar agent-based sort of formulation with two stage charts, whether someone is under care or not under care. In other words, are they in a facility receiving care or not? Again, you can think of it as are they sort of in a care process or not right now? And second of all, do they have a health complaint? Are they suffering from a health complaint, or do they lack a health complaint? And right now, just as a thought piece, we've started. Everyone starts with a health complaint. Obviously, we could make it so that. I'm tempted to even say we should do it now, but people could develop a health complaint by just putting a transition in here. Here, when they have a health complaint, they're going to present for care. And over time, once that health complaint is dealt with appropriately, they'll go to the state without a health complaint. So people have seen these sort of state charts before. This shouldn't be anything too confusing. What you'll notice is that the movement between being under care and not under care is dictated by a message, and that message says that they're discharged from a facility. We'll see where that's sent later. Similarly, going from with health complaint to no health complaint is dictated by a message that says cured. Okay. Finally, let's go check out their appearance here. Up here, you'll notice that the fill color. Well, could anyone help me interpret what this says? What is this saying for the fill color? We really don't need those parentheses around this. What is this saying? Can anyone interpret for me what this means? So I think the fill color is given by this. What does this mean? Good. Otherwise, that's right. So that's the color of the circle. Excellent. And for the line width here, we have a similar logic. Anyone want to interpret that for me? What is that saying? The width of the circle, the width of the sort of border of that circle. Good. That's right. So if they're under care, then it'll be a thick border. Otherwise, it'll be a thin border. And if they have a health complaint, it'll be red. Otherwise, it'll be green. Now, obviously, we could start them without health complaint, and we can transition here probabilistically with a race transition or whatever. But for simplicity, I've had them start in the situation with a health complaint. Okay. Let's go now. Run this model, and then we'll see how the other piece of it is going. So if we run this, we should see something like this, and you'll notice that people are presenting for care. Remember, presenting for care was indicated by a thick border on each person, right? Now, what's going on is when they present for care, they come into this process here. And in this process, they walk into a clinic, and they await a healthcare worker. If that healthcare worker is forthcoming in a timely fashion, they're administered treatment. Upon receipt of the treatment, upon receipt of the treatment, they will determine the treatment success. Either it was successful or it was a failure. If it's successful, their health complaint is now cured. They may still be under some sort of post-treatment observation, but then they'll leave the facility, in which case their border will be cleared. While they're in the facility, they'll still have this thick border. While they still have the health complaint, it'll still be red. So here, some people are getting treated. Other people are balking. Balking because it's taking too long to secure care there. So they're leaving the facility, having bypassed the care, just walking out. Think about people in an emergency room.
Now, let's go see how this is materialized. Some people are leaving this facility because of balking without having secured care. Some people are leaving the facility without having been cured by virtue of having a treatment failure. Yes. This is a teaching model. This is not a case study. The last one was a case study, and I'd be glad to provide a paper to people if you're interested in learning about it. This is not a case study. Okay? This is purely a teaching model. I built much of this model about 6:30 this morning. This is just to sort of give you an indication about how these two come together, in part because several teams here are looking to use hybrid modeling, and I wanted to provide a little example of exactly how it would work. Oh, sure. So why would you need this? Well, why would you be interested in a system like this? I can think of several situations which we've worked with in the past where models like this have been of interest. One of the situations which we see recurrently is a situation where the characteristics of the care process dictate representation on the part of individuals. And so you may be thinking about modifications of the care process in a fashion that would, say, speed up the treatment of people, but at the same time would lead to potentially errors being generated in treatment that would lead to the underlying health conditions not being properly addressed, and that would lead to then representation. Now, in a model which purely was focused on the classic discrete event model would focus on this top process and would have no representation of the population itself. And what that would mean is that we wouldn't really have a sense of representation. People would come in, to be processed by the system, they'd leave, but we wouldn't be able to capture the dynamics of the fact that if we treated someone incompletely, they'd be back the next day. And that might mean we wouldn't be able to anticipate the demand for our services accurately because we'd now be having all these repeat cases because they weren't conferred proper treatment. So if you wanted to understand the impact of a treatment innovation that improves treatment reliability or decrease the time for people to flow through with some implications for the treatment conferred, a system that incorporated both a representation of the care process and of people in the population and whether they were, in fact, still in need of care could be very helpful because that would allow you to then track the fact that these people in the population who are still ill, I should have emphasized this earlier, if someone remains ill, they will generally present for care again here. So in other words, if they're still with a health complaint, but they're no longer under care, they will then come back. If they have a health complaint, they're likely to come back to seek care again. So a system of this sort can help us reason about the implication of process innovations. For example, providing extra staff here, lowering bulking. How would that impact, for example, our care load, our demand for care if we could prevent this bulking? People who bulk may come back the next day for care again. If we could prevent that bulking by having an additional person here. Notice there's a number of healthcare workers here. Right now it's a single healthcare worker, and we could change that very readily within the AnyLogic interface here by going up to this and saying, okay, this pool of healthcare workers, rather than being a single person, it's 2 people or 10 people. By doing that, we could examine the impact on waiting times, to be sure, but also on the demand for the service, because some of those people who would have balked will now be treated and therefore won't come back. So a model like this, by linking up a model of people in the
population and their underlying healthcare status that drives treatment, plus a representation of the treatment process, allows us to look at the treatment process with extra clarity, because we're no longer treating it as a solitude that, we just treat these people and get them through. We're now taking into account representation. We also can devise treatment strategies here that recognize special classes of people. For example, the frequent flyers, the people who come back frequently, we may treat them in different ways. And if we want to capture that, we can't do it with traditional discrete event modeling in isolation, because when a person comes in, we don't know if they're a frequent flyer or not. By capturing people here in the population, and counting actually the number of times they come in, we could actually simulate the effective policies that differentiate between an individual with low risk or high risk, an individual according to their attributes. For example, their aspects of their background, their family context, and we might simulate the effect of treating them differently, recognizing that we're going to be able to capture the impact in their subsequent health status in the population and any representation. So a model like this can be useful for reasoning about how treatment pathways end up impacting health status of the population, and how aspects of the risk factors in health status in the population can end up impacting the flow through here of people, both in terms of waiting time and in terms of the quality of the treatment conferred. For both those reasons, it can be useful for understanding the impact of possible interventions. Is that helpful? Okay.
And then can you also change those set times?
Yeah.
Where there's variability, but those set times that can apply, within the treatment.
That's right.
Or let's say one clinic has different wait times than another.
That's right.
So you can apply that differently.
That's right. I mean, one thing I haven't shown here is shown in some other models I provided to you in the same folder is, suppose you had multiple clinics, and suppose different people in the population would be drawn to different clinics based on, among reasons, wait times or quality of service. You could actually capture that with different people going to different clinics. If one clinic had a process innovation which led to increased wait times, it might lead to those people going elsewhere. You can capture exactly those factors, and most importantly, from your comments, if modifications in the treatment pathway that we could offer, and we could trace the ripple through effect on the people in the population and subsequent representation. And so a very important point here that I want to emphasize is this treatment pathway is not merely downstream of the population. Specifically, you'll notice here that, and I'll stop the model to show this, that this point where treatment has been attempted, after that we basically say, okay, with in this case 90% probability someone is cured, otherwise they're simply viewed as having completed treatment. And in fact, this doesn't even need to be there, because we tell them that they've completed treatment later in the whole process, that they're discharged. The point is that only in some cases are they actually cured. Only in some cases are they actually conferred successful treatment here. This interacts directly with the person. We send this person. Where have we seen this before? We've seen this exact sort of thing somewhere before, in this very room. Where have we sent people a message? Does anyone remember? In fact, yeah, when we have sent messages to people for affecting them in terms of attitudes or beliefs or infection status, exposing them to pathogens, we sent them a message. Here, we're actually changing the health state of the agent. If treatment is successful, we tell them they're cured, and how do you think that affects them? We send them this message here, and how do you think that affects the person here? Where would that message be relevant? If they're truly cured from the health state, where would it affect them? Which lead state? Yeah, with to without treatment. If they're sent that cured message,
if the treatment was successful, as it is with 90% probability, they receive this message here, and now they have no health complaint anymore. On the other hand, everyone who presents for that care process is leaving via this exit, and they're sent a message that says discharge. Where do you think that affects them? Where do you think the discharge message is handled here? Well, it goes from under care to non-under care. So they're in the state of being under care. In other words, they're in a facility right now, say in a clinic, and then they receive this message, and now they're no longer under care. They're back in the population, they're discharged. Why do we keep track of this, whether they're under care or not? Well, among other things, we don't want them presenting for care multiple times. We want them to remember, hey, I'm in this thing, I'm not going to go, present for care again. When they present for care, they go to the facility, we keep track when they're in the facility so that we don't have to go twice or some silly thing like that. When they're already in it, they probably go again. So here's the distinction whether they're in that facility or not. In other words, are they in this process at the top here or not? In other words, are they currently in this process or not? That's what's kept track of by, and we can drill down here by this situation. So this person is located right now somewhere, is up here, as well as being in the population. And when they complete this, they're going to go through a transition where they're no longer under care. Hopefully their health complaint, if treatment is successful, as judged by this, and you notice, here one person has been successfully treated, one person not successfully treated. Here 8 have been successfully treated, but 1 treatment failure, 2 treatment failures, and that's causing them, some people are not being properly treated, and therefore they're not going back to this state without the health complaint. So this person we're seeing here may simultaneously, they're not under care right now, other people will be under care, and will be actually going through that healthcare process. So this is a hybrid model between agent-based modeling, with agent-based modeling capturing people's movement within the facility, or within the population, and discrete event modeling capturing their movement through this process. Any questions about this? Oh, I would note one more research question, by the way, which for which this would be useful. A key motivation for this is obviously a highly small, sort of a very simple process. But if we wanted to change resource availability, if we want to say, suppose we have 3 healthcare workers or 5 healthcare workers, how would that affect, the health of the population? Or how would that affect our treatment load, our demand for services? This is the place to do it. We just go in there and change that from one thing to the other. Okay? Question?
I have a question because when the transition is a message,
Yes.
so what does it mean in terms, like how does the computer know that you should move from this state to this state?
Okay.
Because with a rate, for example,
Yep.
knows that, with the certain rate, it will move from one state to
Yep.
another. However, with the message, I can't really picture, like how does it work in terms of...
Right. So good question. So what you're saying is, like with a rate transition, okay, with this rate, it can sort of roll a dice, so to speak, and pick out when they're going to go. But with this one, how does that work? How is it that when they get a message, they actually, it knows to sort of get them to go, right?
Right.
So, well, I'll give you a hint here. Among other things, if you go look at person, if you go look at the characteristics of person, what you can actually find is that, I think it's in the advanced area, unless they've moved it. Maybe, okay, I guess they took it out in this version. There's actually a place where you can get them to capture the message coming in. So basically what happens behind the scenes is that this thing, so this person is represented as sort of this object. It's represented as this thing that
working there. And basically, you go and you tell it, hey, you have a message coming in. And if it's in a state where that it can receive a message, it will look at that message and say, hey,
Does this message one of those that I can handle?
for example, this one here specifically handles
The a specific message. It handles a cure message.
a discharge message here. This is called
Discharge, not cured. I don't know where that came from. Discharged. Discharge.
And so here, if you're in a state, this message comes in, you tell them, hey, you have a message. So it'll say, okay, what's the message? And it'll say, message is discharged. It'll say, am I in a state which can take a discharge message? Yes, I am. Okay, then I will now go to this other state. So it requires actively telling the agent, the representation, the agent, you have a message waiting. You should get onto it.
So does this mean every single person in the population who's under care will receive this message?
No, no.
It's sent to a good question. Very good question. So this message is sent to a and this you'll find multiple lectures of mine online on discrete event modeling, and that those would explain this in greater detail. But basically, you'll see that says entity send cured to entity. What this is saying is it's sending the message cured to the particular person who has gone up that route up here. In other words, this a person who has gone and flown through here and has gone up here, that particular person has sent the cure message because they've reached this point. A person who goes the other direction, the false direction, is not done. Nothing is done for them. They just go here. They're not sent the cured message. So this is describing what to do for a particular entity who has ended up here. So it's sent just to that person who has just completed treatment and has rolled the dice and has found they were given a successful treatment, which is the case with 90% probability. Then they go up here and they're sent this message saying, you have a message waiting that says cured. That's
Okay, so then the
Yeah.
first part
yeah.
where it says
Yeah.
under care
Yeah.
is the person inside the end of so that I'm trying to
Yeah.
see the relationship between this,
Good.
system
Right.
and this state part.
Yeah.
So the-
So Kurt might also have views on how to characterize this well. This is a very good question. It's a little bit. It requires a little bit of sort of a broadening of how we're thinking about it, because there's a given person, and they're simultaneously in one of these states and one of these two states, right? They're in exactly one of these states, and they're in exactly one of these states, right? At a given time. If we're to freeze them in time, they'll be in a certain state here and a certain state there.
They will simultaneously may also be, and particularly if they're in this state, they have actually, when they go under care, they actually place themselves here into this clinic. So they're still a population member. I mean, if I go walk into the emergency room here, I'm still a population member. I still think that. And so they're still a population member, but now they're in this clinic as well. They just happen to be in this clinic process, and they'll go through this clinic process. At some point, they'll come out of it, and that doesn't stop them from being a full-blown population member. But during this process, they're under care, And when they get discharged here, when they get cured, if they get cured, then they would go to without health complaint, but they'll still be in the process. It'll just update their state to be without a health complaint. And if they are discharged here, then they will be going to the not under care state. They'll be going this way. Does that make sense?
and so it's like I happen to be in this clinic, and they they extract my tooth, right? They pull it out, and that alters my state, and I'm now without the health complaint. I had a toothache and now I'm without the health complaint. And then after some period of observation, they discharged me and my state is no longer under care. But, and now I walk out of the clinic, but I'm still, still a population member. I'm not altered while I'm in the clinic. I'm just, for a certain amount of time, I'm in the clinic. Now, this is an important difference from classic discrete event modeling, because classic discrete event modeling, this is the sum history of an agent's life and so on. So we don't have that history information on them unless we somehow keep them circulating within it. But here, they always stay in the population. Does that help?
Yes.
Okay. And in general, this sort of modeling is very useful. Like some of my colleagues in Australia have used this to characterize the catchment basins for healthcare facilities.
The idea being that, if you're running a hospital or a healthcare facility, the processes in that hospital or healthcare facility, or maybe it's a public health clinic or what have you, they're serving a certain subset of the population. And, people will be coming into that facility based on their health status. They'll be treated in that facility. Their health status will be dependent on how well they're treated in that facility and how long it takes, because they'll balk after a certain amount of time, potentially. So balking in this situation is accomplished by specifying, a sort of a balking time, which can be picked randomly for different people, for example. Here we have a balking time that is given by, here it is, enable exit on timeout. So this particular person, they have a certain limited patience, and if it lies between 20 and 60 minutes, they'll sort of balk if they don't get care within that time. And so that care process affects their health in the population, and different people might go to different facilities based on their reputation, their experience with the facility. And you can capture all of that here. A person in this population, an agent, can remember how long they waited in a facility and choose accordingly. Or they can spread via the social networks. They can spread information about, their experience in different facilities, how long they had to wait. One person could, in principle, tell another, what's been your experience in these two hospitals, which involves more waiting or what have you. Does that help? Okay. That was a different form of hybrid modeling, but one also enabled. Any questions? No? Okay. Yes. So very good question. All three of the types of simulation I'm talking about here can use the cost-effectiveness analysis. Cost-effectiveness analysis is often performed with even simpler model types that are static in character and that don't really capture dynamics. So there's a considerable history of doing very rough and ready cost-effectiveness analysis with static models. Some of the early models of HPV vaccination cost-effectiveness were done with models that don't even simulate transmission in the population. So cost-effectiveness analysis can be conducted with different scopes in the analysis, different levels of investigation, and any of the three types can be used here. Discrete event modeling is best. Its natural tone is depicting health care processes in the health area. So if you want to assess cost effectiveness of a procedure or of a certain healthcare process innovation, you could use a discrete event model as a key portion of it. But in as much as you want to capture the health effects over the longer term in that context, coupling it with an age-based model, for example, would be a very natural fit. Does that help? Help? Okay, very good. Other questions? Okay. There's quite a few other hybrid models that I've incorporated. You're welcome to look at them. I'm also happy to talk with you about hybrid strategies. As I say, I think it's one of the most attractive features of this particular modeling tool.
and it's one which really does sometimes allow you to use the hammer for the nails, the screwdriver for the screws, and the saw for the, for the 2x4. So it's a very useful, level of flexibility that's conferred by the ability to mix and match these sort of models. I hope I've conveyed to you that building these sort of hybrid models is not terribly more hard than building, like this model, it's not terribly more complex than building an agent-based model by itself. It's just conceptually it has different types of pieces in it. Okay, so, question?
Quick question, and
Yeah.
I'm not sure if this question any sense at all, but that makes sense. So how much, I know that the system dynamics model is associated with pain,
Uh-huh.
right?
Yep.
And
In a performance standpoint?
right.
Yeah, yep.
And,
It can run faster.
yeah, so
Yeah.
my question is, how much faster, what importance do we place on having a hybrid model as opposed to maybe
Oh, I see. As opposed to doing it purely in agent-based system, or?
right, and again, this question is maybe
Yeah.
to make more sense because it was very pregnant, but are we talking about 10% savings, resources in terms of time
No, I think, it's a very good question.
and?
Um,
Stupid question.
no, it's a good question. And it varies some by particular model. Because it was just, it's a really good question. Uh, I would expect at least a factor of two. If you're talking about representing an entire population versus a small subset of the population in an agent-based attack, I think we're talking integer factors sometimes. But it depends a little bit on the texture character of the situation. Like that agent-based model, that system dynamics model we had as coupled to the agent-based model, it's actually fairly detailed. Quite cleanly done, but fairly detailed, and really capturing that in an agent-based context would add a significant amount of overhead. So given that we're talking about 80%, more than 80%, 85% of the population would probably be non-diabetic. Representing all of them as agents might double the model's run time. I could imagine that quite readily. Given that we don't need to, in this case, given the model scope didn't require a lot of detail on those non-diabetics, that was a weighty enough thing that we thought, why do it now? We have the flexibility to do it later. If we wanted to make them all agents, we could do so very readily later. But why not leave them for now since we don't need that? Why don't we leave them that way? It'll be faster to simulate, and then if we want to re-examine that later, we'll bring them into the agent. So given that I was guessing integer factors, 2, 3 times. I'd be surprised if it was 10 times certainly, but 2 or 3 times would not be surprising at all. That was a motivating factor. Is that helpful?
Yeah, very much.
Okay. Sure. Any other questions? We'll be talking in probably a brief way about performance issues with models. Suffice it to say that there's a few performance tricks with AnyLogic and with other platforms too, that if you know them, you can reduce quite dramatically the running times associated with the models as a barrier for analysis. In other words, you should be able to speed them up sometimes by a factor of 2 or 3 just by with certain using applying certain checks. And we'll take a look at that in a brief way in the next day and a half. Okay? Okay. Thanks very much. So it's lunchtime, I think, right?